Limiting reactants. In a chemical reaction, do all of the reactants turn into products? What happens when one of the reactants gets used up? So let's look at what the answers are here. And just to quickly, we'll put no up here. And what happens, we're going to find out. So we're going to start with the reaction with 10 moles of hydrogen and 20 moles of chlorine gas. Which reactant will run out first? We made an allusion to this earlier in the unit where we talked about, hey, there's enough nitrogen here for the reaction to go forth, and said we'd talk about it later. That's what we're talking about now, this concept of limiting reactants. So let's see 10 moles of hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Chlorine, well, you can 10 down here, that has 20. And notice they're diatomic molecules. And then you form hydrochloric acid, or in a gaseous form, and let's see how many of them there are. 5, looks like we have 20 of them, okay? So let's go to the next slide. Before we answer it, let's note that the 10 moles of hydrogen are used to produce 20 moles of HCl. So all of these guys were used up. You can count the each individual hydrogen atom, and you'll find one over there for each one. Were all the moles of chlorine too used up? So look at the picture and come up with an opinion on that. And if they weren't all used up, how many are left over? So before you go to the next slide, pause here and try and answer those two questions. No more HCl can be produced once the hydrogen runs out. Okay, that's over here. And we showed that if you count this, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 hydrogen atoms, 5, 10, 15, 20. Okay, this shows all the hydrogen are there. And we will call that the limiting reactant. It limits the amount of product. Since the reaction started with more chlorine than hydrogen, not all of the chlorine is used up in the reaction. We will call chlorine in this case the excess reactant. There's an excess amount. So let's see. How many chlorines do we need on the right side? 5, 10, 15, 20. And if we look at this bunch here, even though it's diatomic, right, we have 20 chlorine atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's all we need. This is the leftover chlorine not involved in the reaction. Okay, so that just stays as chlorine. It doesn't contribute to the HCl. It just floats around more as chlorine gas. And how many atoms are there? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 atoms, or 10 molecules of chlorine. That is the excess reactant. Hydrogen is the limiting reactant. The limiting reactant, sometimes called the limiting reagent, is the reactant present in the smallest stoichiometric amount. And again, these are good words, but when we start doing the problems, that's when you really understand it. It is not necessarily the one with the smallest mass. The limiting reactant is the reactant that you'll run out of first, and that is the one that determines the maximum amount of product that can be made in the chemical reaction. Limiting reactant or reagent, the words can be used interchangeably. These problems are worded differently because the quantities of both reactants are given. Here's an example. 10 moles of hydrogen and 20 moles of chlorine react to produce HCl. Which quantity is the limiting reagent? It's your job, should you choose to accept it, to figure out which reactant is limiting, because that will determine the maximum amount of product you can get. And another name for that is maximum yield. There's a variety of methods to figure out which reactant is the limiting one, so let's start on them. Always good to have a process, and a process consists of a number of steps to get you to an answer. So first, convert the given quantities into moles. Well, that's normally what we do with any of these problems. Those are the initial amounts of each reactant, in moles, very important. Divide each one of them by its stoichiometrical coefficient, well, that's just the number in front of the molecule or the chemical, from the balanced chemical equation. This factors in how much you need for the reaction. Whichever reagent has the smallest quantity from step 2, not step 1, it's not the one that has the least amount of moles, It's the one that has the least amount of moles divided by that stoichiometrical coefficient. Okay, so whichever one has the smallest quantity from step 2 is the limiting reactant. And again, we have to work problems to really make this clear. Calculation time. When 10 grams of hydrogen react with 3.4 moles of nitrogen gas to make ammonia, which substance would be the limiting reactant? So here is our balanced chemical equation. We always start with that. And we convert all values to moles. Well, look, don't even have to do nitrogen. They told us what that is, so that's fun. But let's look at nitrogen. 10 grams of hydrogen, H2, 1 mole of hydrogen. We use the atomic mass unit to come up with the molar mass. 2 hydrogens, 2 grams, multiply. We have 5 moles of hydrogen and 3.4 moles of nitrogen. And let's see the next slide to continue this. Step 2, again, following our process. Find the stoichiometrical equivalence of each reactant. So how do we do that? Here's our balanced chemical equation. We take the moles of each one. This here is nitrogen. So let's label that nitrogen. We found on the previous slide there are 3.4 moles. We divide it by the stoichiometrical coefficient in front of the nitrogen, which is 1. 3.4 divided by 1, 3.4 moles. Then we go over to the hydrogen, that's right there, 5 moles divided by this coefficient here, 3, and you get 1.66 moles. So there is less hydrogen gas using this method with this stoichiometry. It will be the limiting reactant. So hydrogen limits how much ammonia we're going to get. Let's try another example. We have 10 moles of hydrogen gas, that's good, they already gave us the moles, and 7 moles of oxygen, also good, which is the limiting reactant. So step 1, both amounts are already in moles. Step 2, divide each mole by the stoichiometrical coefficient. There's 2 for hydrogen, 1 for oxygen. So here's hydrogen. We take the 10 moles, divide it by 2, see that 2 over there, and we get 5 moles of hydrogen available. Then we go to oxygen. We start with 7 moles, and we take that 1 down. 7 divided by 1, 7. So there's 7 moles of oxygen. So hydrogen gas is the limiting reactant. Oxygen gas will be left over, and we're going to call that the excess reactant. There are often several different ways to solve a problem. The following series of steps is another means for determining the limiting reactant. Step 1. Convert the given quantities into moles. These are your initial amounts of each reactant. Step 2. Use a mole ratio of stoichiometric coefficients to convert the moles of one reactant into the moles of the other reactant. This is the amount of that reactant that is required to completely react with the other one. Step 3. Compare the result from step 2 to the result from step 1. If the amount required, that is step 2, is smaller than the initial amount, step 1, then that reactant is limiting. If the amount required is larger than the initial amount, then the other reactant is limiting. Now solve the first example again using the alternate method of finding the limiting reactant. Example: when 10 grams of hydrogen react with 3.4 moles of nitrogen gas to make ammonia, which substance would be the limiting reactant? So we write our equation right here, balanced equation. Step 1, convert all values to moles. So 10 grams of hydrogen, 1 mole of hydrogen is 2 grams of hydrogen, so we get 5 moles of hydrogen. So our initial amounts are 5 moles of hydrogen and 3.4 moles of nitrogen. Step 2. Choose a reactant. Use a mole ratio of stoichiometric coefficients to convert moles of that reactant to moles of the other one. Once again, our balanced equation. We'll start with nitrogen. 3.4 moles of nitrogen times 3 moles of hydrogen over 1 mole of nitrogen. That gives you 10.2 moles of hydrogen. This is the amount of hydrogen required to completely react with the 3.4 moles of nitrogen. What if we chose hydrogen to start with? 5 moles of hydrogen, 1 mole of nitrogen to 3 moles of hydrogen, and we wind up with 1.7 moles of nitrogen. This is the amount of nitrogen required to completely react with the 5 moles of hydrogen. It was not necessary to do step 2 twice. Step 2, however, was done with both reactants to show how the same result in step 3 no matter which reactant was used in the calculation. So step 3. Starting with nitrogen, we found that 10.2 moles of hydrogen gas are required, but only 5 moles are available. Since there will not be enough hydrogen to react with all of the nitrogen, hydrogen will be the limiting reactant. What if we started with nitrogen? We found that 1.7 moles of nitrogen are required, but 3.4 moles are available. Some nitrogen will be left over, meaning that once again, hydrogen will be the limiting reactant. Regardless of which reactant is used to start step 2, the same conclusion is reached. While both methods yield the correct answer when no errors are made, obtaining the final answer using the alternate method is not always as obvious. While working step 3, it is important to remember which amounts are being compared. If the required amount is larger than the given amount, then the reactant is limiting. 3. If the required amount is smaller than the given amount, then the other reactant is limiting. Choice of which method to use is personal preference. In a car engine, octane, C8H18, is combined with oxygen to produce carbon dioxide and water, which is then exhausted out the tailpipe. The mix of octane to oxygen must be just right, or the engine will run too rich, too much octane, or too lean, not enough octane. If 0.065 liters of oxygen is being mixed with 0.0061 liters of octane at STP, calculate if the mixture is running lean or running rich. Here's our reaction. Methane plus oxygen yields carbon dioxide and water, and we're given 0.065 liters of oxygen and 0.0061 liters of octane. So the first thing we have to do is find the amount of moles of oxygen. So we have 0.065 liters of oxygen, and 1 mole will be 22.4 liters. So we have 0.0029 moles of oxygen. Then find the stoichiometrical equivalent of oxygen by dividing the amount of moles by the coefficient in the balanced equation. Well, here we have a 25 in front of oxygen, so we divide the number of moles by that, and we get 0.000116 moles of oxygen. Next, we find the amount of moles of octane. So here's how much octane we have. Here's 1 mole per 22.4 liters. And we get 0.00027 moles. We divide that by the coefficient in the balanced equation. So our octane has 2. So we divide it by 2, and we get 0.00014 moles. The stoichiometrical equivalent is the amount of the reactant that is available for the reaction. There is 0.000116 moles of oxygen available, and 0.00014 moles of octane available for the reaction. Since there is more octane available than oxygen, the mixture is too rich. A note about the liters to mole conversions. While the 22.4 liter to mole conversion cancels out in the overall process, it is still important to do all the steps. In this case, the correct answer will be obtained, but this only works when both reactants are given in liters. Since this shortcut only works for one particular scenario, it is recommended that performing all the steps be done consistently.